In this video, we get into a little more detail on two very common types of sequences. One of them is called arithmetic, and that means you add the same amount each time you generate another term. So I'm really looking at this kind of as a recurrence relation. I mean, an is going to be the previous term plus some constant every time. The second type is a geometric sequence, and that means you multiply by the same amount each time. And again, as a recurrence relation, that means the next term is generated by taking some constant that I'll call r and multiplying the previous term. So let's look at a couple examples of these. In the first one, I want to expand this sequence 3n minus 4. So I have a function that generates the an's. And I'm going to plug in n equals 1. And I get negative 1. So 3 times 1 minus 4 is negative 1. Plug in 2 and I get 6 minus 4, that's 2. Plug in 3 and I get 9 minus 4, that's 5. Plug in 4 and I get 12 minus 4, that's 8. And so on and so on. And I can see that this is an arithmetic sequence because I'm adding the same amount each time once I start at that starting point of negative 1. So if I look at adjacent terms in the sequence, it's always adding or subtracting the same amount. So plus 3, plus 3, plus 3. Let's look at another example of an arithmetic sequence. Okay, in this one, I can see that I'm adding 2 every time. So plus 2, plus 2, plus 2, and so on and so on. And the way I can get this done with an explicit formula is by putting a 2n in the formula. So that's our goal here, is to rewrite this with an explicit formula, just kind of the reverse of the first example. So if n is 1 there, I get a 2. If n is 2, I get a 4. If n is 3, I get a 6, and so on. So this little piece is adding 2 every time. The only question is, how do we get our starting point correct? So when I plug in n equals 1, I've got to start at 4. So n equals 1 plugged into this, that gives me 2. I've got to add 2 to that in order to start at 4. And then I'll just check my work. So real quick, that's what it looks like with an explicit formula. I plug in n equals 1, and I get 2 times 1 plus 2, that's 4. Plug in n equals 2, 2 times 2 plus 2, that's 6. Plug in n equals 3, 2 times 3 plus 2, that's 8, and so on. So it's working. Let's look at some examples of geometric sequences. In the first example, I've thrown in a little tweak to the notation. Notice here that I started at n equals 0. There is no problem defining a sequence that way as long as it's clear to the reader that we're starting at 0 instead of 1. So I put it in right there. If I sub in n equals 0, I get 2 times 3 to the 0, which is just 2. My next term, I plug in n equals 1, and I get 2 times 3. I'm just going to leave it that way for a second. Plug in my next one, I get 2 times 3 squared, 2 times 3 cubed, and so on and so on. Okay, so that's 2, 6, 18, 54. And again, the defining characteristic of a geometric sequence is that I'm multiplying by the same amount at every step. So I took 2 times 3, and I got 6. Multiply by 3, and I get 18. Multiply by 3, and I get 54, and so on and so on. So there's the expanded form of that thing. In the next example, we go the opposite direction. I want to write the sequence 4, 2, 1, 1/2, etc., with an explicit formula. So what's happening here is that we're dividing by 2 every time. Or I could say I'm multiplying by this common factor of 1/2 every single time. All right, so how do we get it written as an explicit formula? I want the thing to start at 4. And then want to multiply by 1/2 every time n ticks up by 1. So one way to do this is to just write down 4 times 1/2 to the nth power. So if I plug in n equals 0, I would just get 4. If I plug in n equals 1, I get 4 times 1/2, which is 2. Plug in n equals 2, I get 4 times 1/4, which is 1, and so on. And that works. But frequently you'll be expected to rephrase something like this so that it starts from n equals 1, so that we're just dealing with the positive integers. And so I can change the starting point of a sequence by just changing my index n to n minus 1. And then I'll start at n equals 1. And that makes that a 0 exponent, and I'll still start with 4. plug in n equals 2 and the exponent is 1 and my next term is 2, and so on. So that works.